Great. Thank you all very much for attending my thesis defense. I agree this is somewhat surreal, but also fantastic to have you all here. And I've actually never given a talk to so many people I like before. So today, this is a talk about inequality. And as motivation, I'd like to start by noting a couple facts. The first is that our society remains deeply unequal. You see this along virtually every demographic dimension, from race to socioeconomic status to gender. I suspect that if you're here, you already know this, so I'm not going to belabor this point. Slightly less well known is the fact that computer science can exacerbate this inequality, and you see this across diverse fundamental domains. We see this in language processing, for example. When we try to train language algorithms on text that's written by humans, the algorithms learn undesirable stereotypes from the text, like man is to computer programmer as woman is to homemaker. This isn't surprising, since algorithms pick up patterns of all kinds, but it's a big problem if you then use these algorithms to, for example, screen resumes, and they rank women's resumes as less good for computer science jobs. We see this in computer vision. This is a picture of Joy Buolamwini, an MIT researcher who realized she had to wear a white mask for an algorithm to detect her face. In subsequent work with Timnit Gebru, she's shown that algorithms are more likely to misclassify the gender of darker-skinned women. We see this in healthcare when a widely used algorithm used to predict health risks exhibits racial bias. Black patients with a given risk score are sicker than white patients with the same risk score. This bias occurs because the algorithm is trained to predict cost as a proxy for health, and Black patients who have unequal access to care have less money spent on them than equivalently sick white patients. In general, so many similar examples have cropped up in recent years that literally multiple books have been written on this phenomenon. The overall message is simple. Far from being a panacea to social inequity, computer science can actually exacerbate it. This dissertation, though, pursues a more optimistic counterpoint, that data science and machine learning properly applied can also reduce inequality. Given our role in increasing it, this represents not just an opportunity, but an obligation. Specifically, today I'm going to be telling you several stories. In the first half of the talk, I'll talk about how we can use data science to improve healthcare for underserved populations. I'll start by talking about how we can use machine learning to understand racial and socioeconomic disparities in pain, and then I'll talk about how we can use them to understand women's cycles and women's health more broadly. In the second half of the talk, I'll tell you how we can use a statistical approach to detect bias in human decision-making, focusing on policing as an application domain. All right, so let's get right to it, and let's talk about understanding racial and socioeconomic disparities in pain. This is joint work with David Cutler, Yuri Leskovic, Sendel Mullainathan, and Ziad Obermeyer. So a general fact about pain is that disadvantaged groups experience more of it. You see this for socioeconomic disadvantage across a variety of settings, across multiple types of medical conditions, multiple continents, multiple data types. It's quite a robust finding. And you see it for racially disadvantaged groups as well. And this is also true in the condition I'll be talking to you about today, knee osteoarthritis, which is one of the most common causes of disabling pain in older adults. Odds are good that multiple people listening to this talk will develop it if they haven't done so already. Mechanically, what's going on is that with the wear and tear of time, the cartilage between your knee bones erodes and the bones get closer together, they grind together. This causes a lot of pain. And in this condition, as in other conditions, disadvantaged groups have worse pain. Now, a natural explanation is like, oh, maybe they just have more severe osteoarthritis. But here's the interesting thing. These groups have worse pain, even when we control for how severe the doctor thinks their disease is. So I want to make that numerically precise for you, but for you to understand what the numbers mean, I have to tell you how we measure severity and pain. So how do we measure severity? Basically, a doctor looks at an X-ray of the patient's knee. Doctor means radiologist here. And they'll assess it on a bunch of clinical features of osteoarthritis, like how much narrower has the joint space gotten, and then they condense those features into a single summary grade that ranges from 0 to 4. This is called Kellgren-Lawrence grade, or KLG. And so it's a 0 to 4 measure based on examining the X-ray. Now, how do we measure pain? We ask the patient a bunch of questions, like how much pain do you do when doing various activities? And then the patient's answers to those questions are aggregated into a single number, which is called Coos pain score. All the data I'm going to be telling you about today comes from the Osteoarthritis Initiative. This is a study of people who either have osteoarthritis or are at high risk of developing it. And we're going to be comparing pain by 3 binary groupings. We're going to be comparing Black to non-Black patients, and almost all the non-Black patients in the data set are white. We're going to be comparing lower to higher income patients and lower to higher education patients. So what do I mean when I say disadvantaged groups have more pain? So here what I'm showing you is a vertical histogram, pain on the y-axis, and so lower scores indicate worse pain. And you can see that there's an immediate striking visual disparity between Black and non-Black patients. If you want to summarize the size of that gap, it's about 10.6 points on the Coos scale, about 2/3 of a standard deviation, so a substantial gap. Black patients have worse pain. And you can do this for lower versus higher income, lower versus higher education as well. The gaps are somewhat smaller, but they're still large and statistically significant. No fancy math here, just simple differences in means. So what happens when we control for severity? Does that pain gap go away? It turns out it doesn't. So the graph on the right now is stratifying patients by severity. So severity is on the x-axis, that KLG score I told you before. The important takeaway here is that the orange and blue lines are not on top of each other. There's still a gap in pain, even conditional on severity. If you want to summarize the size of that gap in a single number, the standard way to do so is with linear regression. So we just do a regression of pain on race plus KLG, and then the pain gap is the race coefficient when we control for KLG. And the results of this exercise are shown in the second numerical column. You can see that even conditional on severity, there's quite a large gap in pain, and it doesn't even really get all that much smaller. The final column tells you how much smaller it gets. Basic takeaway being, controlling for severity doesn't do that much to narrow racial and socioeconomic disparities in pain. This isn't just true in our data set, by the way. Other studies find this as well. I'm just showing you these numbers for consistency with our later analyses. The goal of the paper is to explain why this is. Why is there a gap in pain, even conditional on how severe the doctor thinks the disease is? In particular, we're going to try and differentiate between two theories. The first theory we call the outside their knees theory, that there are non-knee related factors which are causing disadvantaged patients to report higher pain even when their knee disease is no more severe. What might such factors be? Previous research suggests many possibilities, everything from like higher life stress to less access to pain medication to even, because pain is a self-report measure, differences in how different groups report pain. The commonality here, though, is that none of these factors can be seen in a knee x-ray. There's something external to the knee. In contrast, there's another possibility, which we call the in their knees hypothesis, namely that there are pain-related ailments in the knee x-ray, which KLG isn't capturing, and if we could capture these physical features, we'd be able to explain more of the pain gap. So under the first theory, there's nothing to be seen in the knee x-ray that could explain these pain disparities, and under the second hypothesis, there is something additional to be found there. So why is the latter hypothesis plausible? Like, is this just some crazy theory we came up with? Here are two reasons. The first is that we don't understand pain all that well. This is true in general, as anyone who's ever gone to the doctor to have pain treated will understand, but it's also true in osteoarthritis specifically. KLG just doesn't explain all that much of the variance in pain. And a possible reason for this is that KLG was developed decades ago in heavily white British populations. So it's plausible, right, that it isn't capturing all the environmental or occupational factors that are relevant to pain in modern and more diverse populations that may live and work very differently. So we're going to try and assess whether there are overlooked physical features in the knee, which would explain the higher pain levels in disadvantaged groups. This isn't just an academically interesting question, although we love academically interesting questions here. It's also a question with concrete clinical implications. And the reason is that whether you get knee surgery depends on whether the source of your pain is in your knee. If you go to the doctor in a lot of pain and she looks at your knee and she's like, "I'm sorry, I can't see anything wrong with it," she's not going to prescribe knee surgery like arthroplasty for an apparently radiologically healthy knee. She's more likely to prescribe non-specific interventions like opioids or other painkillers. In the contrast, if you go to the doctor in a lot of pain and she looks at it and she says, "Aha, I know exactly what's wrong with it, very severe radiologic arthritis, you're a 4 on the KLG scale," then it's much more likely, empirically, that she'll prescribe you arthroplasty, knee replacement surgery. Consequently, if our severity scores are missing true sources of pain within the knee in disadvantaged groups, they may be under-referred for surgery. So what are we actually going to do to test this? Well, we're going to train a deep learning algorithm, a CNN, to search for additional signal in the knee x-ray, which would explain the higher pain levels in disadvantaged groups. How does that actually, what do you actually do? How do you search for that signal? Well, the standard approach to searching for signal in a medical image is to train a model to replicate the doctor's clinical judgment, which here means training the algorithm to predict the KLG score. And this is such a standard setup that, in fact, multiple papers have been written on exactly this task or on closely related tasks. The problem, though, is that if KLG doesn't capture all the pain-relevant features, we don't want to just replicate it. We don't want to set a ceiling of clinical knowledge when, by hypothesis, that clinical knowledge may be incomplete. Instead, then, we're going to train the model to learn from the patient directly by predicting Coos pain score. So to be very concrete, the input to the algorithm is an X-ray of both knees. The output is a knee-specific pain prediction, which we term algp for algorithmic severity measure. And if, when we control for this algorithmic severity measure algp, it narrows the pain gap more than controlling for the clinical severity measure klg, it implies that the clinical severity score is overlooking knee features, which would explain disadvantaged patients' higher pain levels. Okay, so that's the method. Let's talk about the results. Our first result is that the algorithm does in fact find additional signal for pain in the knee X-ray. ALGP predicts pain better than the clinician severity score KLG. It achieves a higher R-squared, the difference is statistically significant, and results for other predictive measures like RMSE or Spearman correlation are similar. But of course, those R-squareds are nothing really to write home about, and that isn't the central question in our analysis anyway, which is, does controlling for the algorithmic severity score in fact reduce the pain gap? And it turns out that the answer to that second and more important question is also yes. Here, the first numerical column is just what I showed you before. How much smaller does that pain gap get when we control for the clinician score KLG? But the second column is new. This is how much smaller the pain gap gets when we control instead for the algorithm severity score ALGP. The final column gives the ratio of the first two columns. So for race, for example, the algorithm narrows the pain gap by 4.7 times more than does the clinician severity score. Results for income and education are similar. The overall implication being that there is overlooked signal in the knee X-ray, which helps explain disadvantaged patients' higher pain level. Of course, you should never fit a neural net without doing lots of sanity checks. Boromir understands this. Hopefully we all do too. I'm not going to tell you about those sanity checks in detail now because I suspect my committee will ask me about them, and you're welcome to at the end as well. But I will briefly say that we spent a lot more time running sanity checks than we did generating those main results. Two accessory results I'd like to tell you about. The first is that using a diverse data set contributes to model performance. So the specific experiment we do is we train the algorithm under two settings: on a non-diverse train set, from which we've removed all the Black patients, and a diverse train set, from which we've removed the same number of non-Black patients. So train set size remains constant. The only variable we're altering is the racial diversity of the data set. And while both these models outperform KLG, using a diverse train set further improves performance in terms of R-squared, but more importantly in terms of the reduction in the pain gap. We see similar results for income and education as well. There's a more general implication here with regard to the design of medical studies. Lack of diversity in patient populations has often been a concern, and this is an empirical demonstration of the fact that that actually matters. It can affect the results that you get. Finally, the clinical implications of these results. As I said, under sort of clinical procedures, we tend to give knee surgery to patients who have two things. They have high pain and they have severe disease as measured radiologically. So we test how the allocation of surgery would change if we measured severity in two different ways, using the clinician severity score KLG and using the algorithm's ALGP. And what we find is that because ALGP gives disadvantaged patients higher severity scores, it is in turn more likely to refer them for surgery. For example, Black patients would be about twice as likely to get surgery if we use the algorithm as opposed to the clinician. This is not, by the way, an argument for immediately rolling this out in the clinic. Obviously, you would have to do a ton of additional validation to warrant that. Rather, it's a way of saying why these results are important from a clinical standpoint. So to summarize, we trained a deep learning algorithm to predict pain from knee X-rays. We showed that our algorithm found overlooked signal in the knee X-ray, which helps explain disadvantaged patients' higher pain, and a concrete implication of these results is that disadvantaged groups may be under-referred for surgery. To put this within broader context of work on algorithmic fairness, there's been a lot of previous and valuable work, as I mentioned, on how machine learning methods can increase disparities in medicine. This is essential work, but we should also keep the more optimistic flip side in mind that machine learning methods can also potentially reduce disparities by detecting signal that humans miss. Key to our results here, key to reducing rather than increasing disparities, are first, we chose a prediction task that didn't merely replicate clinical knowledge, and second, we trained the model on a diverse data set. All right, that's racial disparities in pain. Let's talk about understanding a different underserved population and understanding women's cycles. So cycles are fundamental to human health, and there are a variety of cycles on multiple time scales. We have daily cycles like circadian rhythms, weekly cycles like sleeping in on the weekend, seasonal cycles like getting sadder in the winter or exercising more in the summer, and of course the menstrual cycle. The menstrual cycle itself is a vital sign in human health. It's implicated in a variety of medical conditions from cancer to pregnancy. Unfortunately, stigma and lack of data have hampered study of the menstrual cycle, and this is true across diverse contexts. Data is often lacking from medical data sets. Health tracking apps like Apple and Fitbit have been very slow to add menstrual cycle information. Clinicians themselves don't always consider menstrual health when considering the patient's health. And the broader culture stigmatizes discussion. And to be clear, this is not like some abstruse ivory tower feminist studies thing, right? It results in concrete harm to the health of half the global population. To give you two specific examples on this, the girl on the left is required to stay in that tiny hut outside when she's on her period as a consequence of stigma associated with the cycle in Nepal. And it's not hard to see why this is potentially dangerous, right? Like women have been bitten by snakes, they've been sexually assaulted, they've died of smoke inhalation as a consequence of being forced to go into these huts. The woman on the right is Noemi El-Haddad. She's a professor of biomedical data science at Columbia, and she suffered for much of her adult life with pain from endometriosis, a condition linked with the menstrual cycle, which is still very poorly understood. So stigma and lack of data here really is hurting real people. It's not just some abstract thing. But there is good news here, which is that women's health apps offer new potential for understanding and destigmatizing this aspect of women's health. Specifically, today we're going to be using data from the Clue Women's Health app. This is used by millions of women across more than 100 countries. It tracks more than 100 features daily, including mood, pain, sexual activity, pregnancy tests, etc. So people can log their daily lives and menstrual health in a very rich way using this app. So to give you a sense of what kind of data people can log with this app, this is purely simulated data. This is not a real person for the purposes of privacy. On the x-axis is time, on the y-axis is the kind of thing they're logging. And so you can see people can log like when their periods are starting. They can log continuous features like resting heart rate and weight. And they can also log sort of discrete behavioral or mental features like whether they're having sex or like whether they're stressed or calm, etc. So we're going to use this data set to provide the first decomposition of female mood, behavior, and vital signs into those 4 cycles I was telling you about before, the daily, weekly, seasonal, and menstrual cycles. And thereby, we're going to improve understanding of this fundamental aspect of women's health. Our data set consists of millions of women, tens of millions of observations spanning all over the globe. And we're going to be studying cycles in 15 dimensions of mood, behavior, and vital signs. For example, happy versus sad mood or resting heart rate. So how have people previously studied cycles? What they tend to do is take a single population average at each time point. So this is reproduced from a Golder and Macy papers in Science a couple years ago. They're studying Twitter data, and they're studying how happiness fluctuates over time. And so, for example, the value at like 3 p.m. on a Wednesday is just the population average across people at 3 p.m. on a Wednesday. And it's clear that the important trends emerge when you do this. Similarly, here's another study of Twitter data. I'm looking over a longer time scale, and you can see that there are outliers, there are weekly cycles, like all kinds of important things emerge. And we can do this in our data as well. So this is now made on Clue data, and I'm plotting each person's happiness relative to their own baseline, over time. And you can see important things emerge from this kind of analysis, right? So that high frequency fluctuation, that's the weekly cycle. You can also see outliers, so those green dots are Christmas. The purple dot, this is true, I did not make this up, is the day after the 2016 US election. But there's a problem with this type of view as well, which is that averaging makes the menstrual cycle invisible. And it's not hard to see why this is, right? If you take a population average of all people on January 1, everyone's going to be at a different point in their cycle on January 1, and so that source of variation is going to be averaged out. You're going to make the cycle invisible. Turns out this is pretty important. The red line here plots the counterfactual, where you actually could observe that menstrual cycle variation. In particular, that happiness cycle amplitude is about twice the Christmas effect and half the US election effect, so it's really quite substantial. So how actually did we get that red line? Well, here's how we decompose people's variation into 4 cycles. We're going to use OLS. Specifically, our observations here are going to be mood for one person at one time point, and we're going to regress that dependent variable on categorical variables for hour of day, day of week, month of year, and day of menstrual cycle. So we're regressing it on 4 different types of variables. And then the regression coefficients are going to capture each of the 4 cycles, the daily, weekly, seasonal, and menstrual cycle. Let me show you an example of what I actually mean by this sort of analysis. So here, I'm plotting the regression coefficients for each of the 4 cycles, menstrual, daily, weekly, and seasonal. And the menstrual cycle is on the left, and you can see that the amplitude of that cycle is actually larger than the amplitude of the other 3 cycles. For happiness, for example, it's 1.4 times the amplitude of the daily cycle. The overall implication being, this is why menstrual data is important. Without it, the largest cycle for this dimension is invisible. This isn't just true for happiness, by the way. Now what I'm plotting is the amplitudes for all 15 cycles that we study in our data set. So it's that max minus min of the regression coefficient curve. And the menstrual cycle is the red bar, and you can see that it's generally the tallest of the bars. In particular, it has the largest amplitude for 11 out of the 15 dimensions that we study. It persists not just across dimensions, by the way, but also across cultures. So here what I'm plotting, each country is in blue if people tend to get sadder prior to their period. It's in red if they tend to get happier immediately prior to their period. And you can see that all the countries are blue. So this is a directionally consistent effect. It's not specific to a particular culture. Yeah, so it would be easy to look at these results and say like, oh, so you're saying that women have this important cycle that men don't have, so therefore they're more volatile. No, that's not what I'm saying. In particular, our analysis makes no comparison across genders or sexes, right? And previous research does not find sex differences in volatility. There's this great paper entitled "Female Rats Are Not More Variable Than Male Rats," clearly by an author who's quite irritated with this trope. And there's some simple reasons for this, right? The first is that men themselves have hormone cycles, and another is that cycles, of course, are not the only source of volatility in human mood or in other dimensions of human behavior. I could also note that anyone who's ever seen men at a football game would not conclude that women are more volatile, but I'm not going to make that comment because my entire dissertation committee is male. So to summarize, stigma and lack of large-scale data have hampered study of the menstrual cycle, but this invisible cycle is actually a primary contributor to cyclic variation. And the good news is that new women's health data sets offer us the unique potential for understanding it. All right, let's move to the second half of the talk, which is about detecting bias in human decision-making, specifically policing and and traffic stops. So like, why are traffic stops even something we care about? Well, they're one of the most common ways Americans interact with the police. Tens of millions of people are stopped every year, although I imagine that number is somewhat lower right now. And there's concern that traffic stops may suffer from racial bias. To be clear what I mean about racial bias or racial discrimination, and I'll be even more precise about this in a bit, this is when someone is treated more negatively because of their race. So you're stopped by police because you're Black. They wouldn't have done so had you been driving identically, behaving identically, but you've been white. Obviously, this is very bad if it's happening. It's hard to statistically test for, though. Let's talk about why. So first challenge we confronted when we embarked on this project is that there was no unified national data set which tracked every stop made by the police in the United States. So we set about creating such a data set, and we did so in two steps. In the first step, our journalist collaborators submitted data requests to more than 150 police departments over the course of 5 years. Journalists are amazing, by the way. And then in the second step, all that data comes pouring in, right? And it's in a million different formats, right? Many different data formats, whatever. And this is like literally a nightmarish data standardization task. And I say nightmarish quite literally there in the sense that like I woke up from nightmares about the data while we were working on this project. There's no shortcut here. We had to put in thousands and thousands of hours in order to clean this up. This was hard work from a lot of people. But the good news, not going to talk about that at all, is that we've made all the data and code available. You can download the data yourself and do analyses on it. And please do that, because I think a single analysis can only scratch the surface of what is possible here. Our full data set encompasses some 255 million stops, and those come from both city agencies, so that would be things like the LA Police Department, and they also come from state agencies, that would be the California Highway Patrol. In the main analysis I'll be talking to you about today, we analyzed 95 million records, and that number is somewhat smaller for a couple reasons. First, we filter for white, Black, and Hispanic drivers because many other race groups are quite small in many of those states. Second, you had to filter for departments that have data of sufficient quality to even enable you to analyze the data. So like if a department doesn't track race at all because we don't racially discriminate, so why would we do that? Obviously that makes it much more difficult to analyze racial discrimination. And finally, we filter for stops between 2011 and 2018 to impose some standardization in the time period. So our analysis looks at three questions. It looks at whether the police discriminate in whom they stop in the first place. Second, do they discriminate in whom they search after stopping them? And finally, how do policy changes, specifically the legalization of marijuana, affect these racial disparities? Today, I'm only going to be talking to you about the second question, and I'll do so because it's interesting from a statistical methods standpoint, but also because the methods are applicable to studying bias in many other decisions. So to give an outline of this part of the talk, I'll start by telling you about simple tests for racial discrimination here and how they're statistically flawed. Then I'll tell you about a more complex threshold test, which is too slow to run on a data set of our size. In the second half, I'll tell you about a new family of probability distributions and how we can use them to create a much faster version of the threshold test, which is more practical to use. So, are police searches discriminatory? A little bit of context on searches. So after police stop a driver, police are allowed to conduct a search. The purpose of a search is to find contraband. That means stuff you're not supposed to be carrying, like illegal drugs or weapons. It can't be to like harass the driver because you're curious what their car looks like or whatever. So the specific form of discrimination we're testing for here is, are minorities searched when they are less likely to have contraband? For example, if the police are searching whites, if they're only 90% likely to carry contraband, but they're searching black drivers, if they're only 20% likely to carry contraband, that difference in thresholds of evidence, that's our definition of discrimination. Importantly, this is not comprehensive. We're not trying to test for all forms of problematic police behavior. This is why it's good if other people do follow-up studies. So a first simple test of discrimination is to look at the search rates themselves. In other words, how likely is someone to be searched after a stop? And the results of doing this analysis on our data are shown at right, search rate on the y-axis, state patrol stops on the left, city stops on the right. You can see that minority drivers are far more likely to be searched after a stop than are white drivers. But this itself doesn't prove that the police are being discriminatory, which is to say, applying different standards on the basis of race to whether they conduct a search. It's possible that some races are more likely to carry contraband. The purpose of a search is to find contraband. So if some races are more likely to carry it, police may be more likely to search them, even in the absence of discrimination. So a second simple test which has been proposed is what's called an outcome test. And the outcome test says, let's not look at how likely searches are, let's not look at the search rates themselves. Let's look at the outcomes of those searches. Let's look at how likely those searches are to find contraband. We call that the hit rate. The intuition here is like, look, if searches of white drivers are finding contraband 90% of the time, but searches of black drivers are finding contraband only 10% of the time, that suggests that police are searching whites only if they're very likely to be carrying contraband, but they're searching blacks more at random. So if hit rates vary by race, that's discrimination under the outcome test. And when you do this analysis on our data, that is in fact what you see. The aggregate hit rate is lower for Black and Hispanic drivers than it is for white drivers. But it turns out there's a flaw with the outcome test as well, and this is called inframarginality. I'll illustrate this using a hypothetical example. Imagine there are two races of drivers, white drivers and black drivers. And among each race, there are two easily distinguishable groups. Maybe one of them is wearing blue hats. There are those who are very likely to carry contraband. And among that group, 50% of black drivers carry contraband, 75% of white drivers. And those who are very unlikely. And among that group, 5% carry contraband regardless of race. And importantly, imagine in this hypothetical example that police are not being discriminatory. They search everyone who is more than 10% likely to carry contraband, irrespective of their race. They're applying the same threshold to all drivers. So what's going to happen to the hit rates for white and black drivers? Well, the police are going to search all the likely looking drivers, and they're going to end up with a hit rate of 50% for black drivers, 75% for white drivers. And so the outcome test is going to interpret that difference in hit rates as discrimination against black drivers. But by hypothesis, there is no discrimination in this world because the police are applying the same threshold to both groups. So the outcome test here is giving a misleading result. It's indicating discrimination when there is none. It can also yield a misleading result in the opposite direction, where it fails to indicate discrimination, even though it is in fact present. So like, why is this happening? It's happening because the statistic the outcome test measures, which is the probability you carry contraband, conditional on being above the threshold, is not the same as what we care about, which is the threshold itself. But the threshold is not easily observable in the data. And so the solution that's been proposed is to use a Bayesian latent variable model to infer it. So now I'll describe that model to you. This is called a threshold test. It proposes a stylized model of the police stop, and the goal of it is to estimate search thresholds that are consistent with the observed data, namely the search and hit rates. Discrimination under this model, as before, is if lower search thresholds are being applied in searches of minority drivers. So here's how the threshold test models a police stop. We imagine that when the officer stops a driver, they estimate the probability P that person carries contraband. P ranges between 0 and 1, and it represents a myriad of contextual factors, the age, the gender of the driver, how nervous they're acting, etc. And P is drawn from a risk distribution shown graphically at right. So for example, if the police officer pulls over a bus driver, hopefully it's quite unlikely the guy is carrying contraband. He's driving kids around. He shouldn't be driving around drugs too. And so P would be quite low. On the other hand, if the police pull over a driver and he's acting woozy and drinking out of a bottle, it might be something innocuous, but it's probably not. And so P would be quite high. Now, in order to fit this model at all, you have to make a parametric assumption about what those risk distributions look like. You can't fit arbitrary distributions because then you would have infinite degrees of freedom. And so the parametric assumption the original model makes is that the risk distributions are parameterized by betas. Now, if P exceeds a threshold, the officer searches the person and finds contraband with probability P. So in the case of the bus driver, he'd be below the threshold. The officer wouldn't search him, wouldn't find contraband. In the case of the woozy driver, he'd be above the threshold. The officer would search him and would find contraband with 75% probability. The model allows the thresholds and risk distributions to vary by race and by location, and discrimination under this model is if lower thresholds are being applied in searches of minority drivers. Now, in order to actually fit this model, you have to specify how you go from the unobserved objects to the observed data. The observed data here are the search rates and the hit rates for each race and location. For example, the search rate for Black drivers in San Francisco is 30%. And the unobserved objects are the thresholds and the risk distributions. So I've shown graphically how we go from unobserved to observed at the right. The search rate is the amount of the risk distribution, the proportion of the risk distribution that lies above the threshold. So graphically, it's the amount of gray mass. Mathematically, it's 1 minus the CDF. The hit rate is what we call the conditional mean. It's the expected value conditional on drawing from the gray mass. So conditional on drawing from the risk distribution above the threshold, what's your expected value? So to complete the Bayesian model specification, we have to put priors on the thresholds and on the risk distribution parameters, right? So we've already specified the likelihood portion of the model. Now to complete the Bayesian specification, we have to put priors on the parameters. Not going to tell you about the priors in detail just because it's fairly mathematically intricate, but our results are not terribly sensitive to the exact form of the priors. Now, by combining those two ingredients of Bayesian inference, right, the priors and the likelihood, you can combine the you can infer the posterior over the parameters, very standard Bayesian inference, and the specific tool we use to do this is Hamiltonian Monte Carlo. Unfortunately, this actually doesn't work at all on a data set of our size. Model fitting is prohibitively slow, so you can't fit a single model on the entire national data set. Why is this? Well, recall that I told you that the risk distributions are parameterized by beta distributions. In order to compute the search and hit rates, you have to compute their CDF and conditional means. Because of the way Hamiltonian Monte Carlo works, you also have to compute the gradients of those quantities. It turns out doing all this is prohibitively slow on a data set of our size. Consequently, fitting a single model on the entire national data set is impossible. Perhaps more importantly, from a practical impact standpoint, the test can't be used by the people who really need it. Journalists, policymakers, police departments, etc. Anyone who doesn't have sort of infinite cores and infinite grad students, which is sort of how I think about Stanford professors, and that really limits the practical applicability of the test. So our solution is to propose fast threshold tests. We describe a new family of probability distributions, which we call discriminant distributions, and we use them to make a test that runs much faster. Like the beta distribution that they replace, the discriminant distribution is a 2-parameter family on the unit interval, but it has some nice computational properties. Consequently, all we have to do is replace the original beta distributions with discriminants to produce a version of the threshold test that runs 2 orders of magnitude faster. Here's how a discriminant distribution works. Here's how we generate a draw from the distribution. In the first step, we draw a binary class variable y. Y is positive with probability phi. You can think of the positive class as representing those who carry contraband, and the negative class as those who do not. In the second step, we draw a real number x, called a signal. If y is equal to 1, then we draw x from a Gaussian which is centered at delta, where delta is non-negative. If y is equal to 0, we draw x from a Gaussian which is centered at 0. You can think of x as sort of a noisy indicator of the probability that someone carries contraband. It's not a perfect indicator, but it gives you some signal. Finally, this is the final step, you compute the posterior probability that y is equal to 1 given that draw x that you observe. Because this is a probability, it will lie between 0 and 1. You can compute it using Bayes' rule, and this is the actual draw from the discriminant distribution. So why is this mathematical exercise worth doing? Here are 2 advantages. The first is that discriminant distributions are a flexible family of distributions. We show that you can approximate a wide variety of logit normal or beta distributions, so you're not really losing representational power here. But secondly, because discriminants are entirely based on Gaussians, and an overriding lesson of my graduate research has been that everything is nice when you use Gaussians, many useful quantities, specifically the mean, CDF, and conditional mean, are very fast to compute. Of course, the CDF and conditional mean are exactly what we need, so all you need to do is replace betas with discriminant distributions in the threshold test to produce a test that runs much faster. We anticipate this will be more broadly useful in statistical inference by yielding speedups in many other domains. Anywhere where you have a beta or a logent normal, it's running slowly, and you could potentially swap in a discriminant distribution if you have to compute quantities like the CDF or conditional. Great, so now we have this fast test. We can fit a national model. This shows the results of doing so with the average threshold plotted on the y-axis. And you can see that the model is inferring that there is a lower threshold of evidence for searching minority drivers than searching white drivers, suggestive of discrimination against minority drivers. So to summarize this analysis of searches, I've shown you three things. I've shown you that search rates are higher for minorities, hit rates are lower, and thresholds are lower. This is a characteristic pattern for discriminatory searches. You'll see it, for example, if you look at stop and frisk data in New York City as well, which whatever Michael Bloomberg might say is very, very, very obviously discriminatory. All three tests here are suggesting discrimination against minorities, but the threshold test is doing so in a way that is robust to statistical flaws, like inframarginality. I mentioned that the same methods are potentially more broadly applicable in other datasets with binary decisions and binary outcomes. To give a specific example of this, imagine we were trying to test for discrimination in loan decisions. The binary decision is, did someone receive the loan? The binary outcome is, did they repay it, conditional on receiving it? And so discrimination against minorities would look like minorities are less likely to receive a loan, but they are more likely to repay it if they receive it. To close by speaking briefly about the public policy impact of this work, I mentioned that one advantage of the fast threshold test is that it's much easier for journalists and other non-academic practitioners to use. And in fact, in October of last year, that was exactly what we saw. The LA Times was able to take our fast threshold test with assistance from our team and use it to show that the LAPD was searching Black and Latino drivers on the basis of less evidence. And in response to this is why I like journalists, the LAPD announced within days that they were going to dramatically cut back on pulling over random vehicles in an effort to reduce this bias. So this is a case where the fancy math quite directly translated into real-world impact. So to summarize the contributions of this project, methodologically, we provide a fast test for discrimination and a corresponding family of probability distributions. We provide a data set which has already been widely accessed, but please download it yourself because I think there's a lot of further analysis that can be done here. And finally, analytically, we provided a large-scale analysis showing racial discrimination in police stops. There's actually a lot of other interesting analysis in the paper, which I don't have time to discuss right now. So let's chat sometime if you're interested in marijuana or beautiful sunsets and what those have to do with police discrimination. Okay, so to summarize what I've told you about today, I've given you several examples of how we can use data science to increase social equality. In the first half of the talk, I gave you two examples of how we can improve healthcare for underserved populations, specifically racially and socioeconomically disadvantaged groups and women. And in the second half of the talk, I told you how we could use a statistical approach to detect bias in human decision-making, specifically with applications to policing. Is it okay if we do acknowledgements before questions? I defer to the whims of the committee chair. Yes? Good. Thank you. Wonderful. Okay, great. So like any good engineer, I did do robustness checks on my acknowledgements, so I'm pretty sure they fit in time and I can deliver them without crying. I've been at Stanford 9 years and I've earned 3 degrees here and I'm still quite in love with this place. I'm still overwhelmed by its beauty. I'm still amazed I was allowed to spend all this time here. I'm still so sad that I won't get to say a proper goodbye. But there's another side to my time in graduate school. The truth is that doing a PhD has been one of the most difficult experiences of my life, a period when I became profoundly disillusioned with the power dynamics in academia, which are often exacerbated by gender and other inequalities, and the harmful treatment they can allow. And I mention this because this is a talk about inequality, and I would feel bad if I didn't say anything, because I know experiences like mine are common. A slew of studies in recent years, including my own work, point to extraordinary rates of depression and anxiety among PhD students. There were times I thought I would leave academia entirely. But instead, I went on the job market and I'll move to New York next year as an assistant professor. And this was only possible because of the efforts of a number of extraordinary people. And so the thing I most looked forward to in the last year of my PhD and in preparing this talk was getting the chance to acknowledge all the people who have helped me along the way. This is the most important talk, actually, to me. So I'd like to start by thanking the people who wrote my letters of recommendation, not just for the letters, but for always being people I knew I could count on. So my advisor, Yurei, I made a cartoon to describe a typical research meeting with Yurei. So I'll come in and I'll be like, Yurei, I built a tower to the moon. And Yurei will be like, great, so exciting. But like, can we make it reach to the nearest galaxy? And I'll be like, Yurei, like that will never work. You know, what about asteroids or aliens or centripetal acceleration or general relativity or whatever? And he'll be like, don't worry, we'll figure it out. And I have to admit, he's almost always been right when he said things will work out. And so I think he's been a great advisor who's always made me feel better about research, because while I tend to see how things can go wrong, he sees how exciting it will be if they go right. And I do think it takes courage to see the world that way. I think it's a lot easier to criticize someone's methodology than to go out and build something yourself. Dan Jurafsky, this is the most recent email I received from Dan Jurafsky. I replaced all the text with lorem ipsum for privacy reasons, but the exclamation points are real. There are 13 of them. The email is 109 words long. I've been asking him for advice for nearly 10 years because he has this gift for getting incredibly excited about your ideas, but at the same time giving incisive criticism, which is spot on. He's just an enormously kind and reliable source of advice. Sendel, at my first meeting with Sendel, he was trying to pitch me on this idea, and I was pressing him on the details, and I asked him to write out the math, and neither of us had a pen, so he proposed that we walk to buy one. This took us like 3 drugstores, 20 minutes, and I'm like, oh man, this was a bad idea. Like, this guy's way too busy and famous to be pen shopping with a random grad student. Once we had finally found a pen, we spent another hour talking through the math. And so after the meeting, I looked at our notes, and I decided it was rare and precious to find a senior academic who was so generous with his time. That's what you want in a teacher, someone who is both phenomenally good at what they do and willing to take the time to explain to you how they do it. That first impression has been accurate, and his advice has been instrumental to the academic and professional decisions I've made since then. Daphne Kohler, I often feel like talking to Daphne is like interacting with a pure nuclear core because she is so intensely brilliant and she doesn't make any effort to shield you from it. I actually met her academic advisor on my job tour, and we spent the whole meeting talking not even about why I should get the job, but why we were both intimidated by Daphne. So I think I'm in good company here. But at the same time, I have also found her to be very kind. I met her when I cold emailed her as an undergraduate to tell her that I had received some bad medical news. She was not even at Stanford full time, but she wrote back on New Year's Day and found me a position in her lab. David, so I've been meeting with David at 8:30 or 9 a.m. every week for the past year. We actually just managed to move the meeting to 9:30, which is very exciting. And he is the only person I know who is always gracious and never grumpy at that time of day. And he's always awake enough to ask sweeping social science questions. It's been a great pleasure to work with him. James Zo's work has always intrigued me as much as any Stanford researcher, and it's been a privilege to have him scrutinize my own. To my teachers, I've had extraordinary teachers since I was about 8 years old. Many of these people sat down with me at critical crossroads in my life and told me that I should try to do the difficult thing I wasn't sure I could do. Chiara Sabati told me I should go in the job market. Noah Goodman told me I should do a PhD. John Dell told me I could learn quantum electrodynamics. I realize now that it's an enormously important use of your time as a teacher to try to nudge young people in the right direction at these intersections. In 5 minutes, you can shape the next 5 years of their lives. And because of these people, I always try to respond when younger researchers reach out for advice. I'm grateful to Rhodes, Hertz, and NDSEG for funding my graduate research, and especially to the Rhodes and Hertz communities. It was a great blessing to find myself plunged into these tight-knit communities of passionate, bizarre, and immensely good-hearted people. I'm grateful to the SNAP Lab. It's full of ambitious people who are nonetheless always supportive and never cutthroat. Grateful to people like Camillo, who I swear has never sat through a talk without asking an insightful question, to Michele, who has put in so much time to keep the lab together and take care of everyone, to Rock, Yesenia, and Adrian, who have been invariably patient and tolerant of my stupid questions. I'm also grateful to older students in the lab who have always intimidated me with their resumes, but never with their demeanors, particularly to Marinka, Hema, and Tim Althoff for mentorship and advice during my job search. My computer is threatening me with dying. Wait 1 sec, I gotta plug it in, sorry guys. All right. There we go. Okay, perfect. I'm grateful to my innumerable exceptional co-authors. This work would never have been possible without them. I'd particularly like to acknowledge my most frequent student co-author, Peng Wei. He's the one on the right. Peng Wei uses his small, fluffy dog and laid-back demeanor to conceal the fact that his mind works at a different speed than most of ours. Sometimes this is jarring, but often when he casually picks up Japanese when you're at a conference in Japan or writes half the proof section of your paper at 3 in the morning, it is quite convenient. Cheng-Woo Lee, this text message is one of thousands of research committee conversations I had with Cheng-Woo over the course of my PhD. Like most of my conversations with him, it involved math, cocktails, and me telling him he was wrong. Cheng-Woo wanted me to get a job as an econ professor more than anyone else did, including me. He made me pancakes the morning before my first talk for an econ audience, and when he learned that I did not have the brand of suitcase he insisted was optimal for the job market, he sent me one the next day. Ironically, for someone who talks like a 19th century British lordling and never uses an English phrase when a Latin one will do, he has always been one of the people who most makes me feel like academia is a welcoming and inclusive place. I am grateful to have been his friend during his transition from world champion debater to political dissident to future Clark medalist. To all my other friends, particularly to my housemates, who taught me the importance of making a house a home, and to my women and non-binary friends who kept me sane in my increasingly male-dominated world. To the Boston Roths and the Berkeley Pearsons, who always gave me a place to stay on the East and West Coasts. Nat is the only person I know who is smart enough to debug a neural net at 3 a.m. and kind enough to try when you've just woken him up. Early in my PhD, when we weren't even dating, I told him I was working on this high-profile police project and it was very important to me that it was correct, and would he please spend an evening reviewing the code with me? The code was written in a language he didn't even know, but he immediately agreed because that's just the sort of person that he is. We started dating a couple weeks later. Not going to make causal claims here, but you can do the math. Last, to my family. To my little sisters, as they've grown into rock stars, I've realized that the great thing about sisters is that your maturity grows with their accomplishments. When I was little, I was so competitive with my little sisters that I used to shove my baby sister, 5 years younger, so she couldn't beat me at soccer. But now that her achievements are actually intimidating, I feel nothing but pride. To my parents, who taught me that PhD notwithstanding, I cannot yet understand how much parents love their children. To all my grandparents, particularly my grandma, who is 87 years old and still reads my scientific papers. It would have been my grandpa's birthday 2 days ago. We were very close. That's us playing chess up there. So he's been on my mind. As I was preparing this talk, I revisited an essay I wrote as he was dying of cancer right before I began my PhD. In it, I promised to spend my PhD trying to cure cancer. And rereading this essay, part of me thought, like, damn, that didn't age well. I've written 15 papers during my PhD, and only one of them is about cancer. I got totally derailed by this equality thing, and apparently I confused cancer with knee arthritis, which is just embarrassing. But then I reread the last sentences of the essay, and I'll give you a moment to read them as well. I think they're about something broader than cancer. They're about fighting to make real people's lives better, fighting to solve problems you know you cannot fully solve. I hope this dissertation has fulfilled that broader spirit. Thank you very much for your attention, and I'm happy to take your questions.